In the next section of our compression chapter, we'll look at the Burrows-Wheeler transform. And is one of these things that look really magic at first sight and unclear how they could help. And then over the time, people found that this is a really, really key step to bringing compression to the next level and also putting it on some more principled legs. All right, let me show you what it is. First of all, the Burrows-Wheeler transform is just a permutation of the letters. So you're given a text and then you jumble the letters around and that becomes the transform. But it's a specific way of doing that, okay? It's not just randomly throwing the letters around. And it happens to be that the output text is much more compressible traditionally by putting the move to front heuristic after the BWT. But there's many other ways to see why it has compressibility features. The slight downside, and yeah, maybe I can give this historical anecdote as well. It needs the whole text to apply this transformation. You can't do it easily in a streaming fashion. So in practice, it's often applied to some block of data, but in principle, you can do it for the entire text. You just need enough memory. This also meant that at the time when this was thought of, when it was invented by Wheeler, he thought, that's a cute idea, but it's completely useless because it's impractical to do. He thought there's no way that we'll ever have enough main memory to make use of that compression technique, so he ditched it. And later, when he had, I think his student, Burrows, he explained that idea again to him. That was then in the mid-90s. And he said, yeah, let's implement this. This should work fine. And it did, at least shortly after that. And it's still using the same memory so there were no theoretical improvements on the idea at that stage, but it became practical because the machines got a little bigger and a bit faster. So it used to be something that people believed is just of curiosity, of academic interest, and a curious algorithm, but then it turned into something practical. And now it's at the heart of pretty much all genome-wide analysis to use something like this transform on really huge data. So it's a nice illustration that sometimes things don't seem practical right now, but often that's only a statement for a certain time, and it can change. As data becomes bigger and bigger, asymptopia comes closer to us in this sense. Okay, but back to the more concrete topic. The BWT became famous for being part of this bzip program. If you have a Unix system where you use the departmental ones, it will usually be installed. It's just bzip as a program, bzip2. It's not as well known as I think it should be. If you take the ASCII text of the Bible, by the way, it's 4 million characters is pretty much the text of the Bible in English. And you can compress this with, well, gzip is some implementation of the zip algorithm. Gets down to a quarter of that. 7-zip, this may be more well-known. Well, hack combining many different heuristics gets it further down, but bzip is even better than that. And that's typical for natural language text. It is slower than gzip by many orders of magnitude, I think, but still fast enough to do on large inputs. So what is the BWT now? That's 2 T's. The BWT transform is the Burrows-Wheeler transform. It is based on the notion of cyclic shifts. If you have a text, then imagine you write it on a circle. Then there's a certain point where the text begins and ends. And a cyclic shift is you just put this divider somewhere else. And I tried really hard to find a string where you can do a cyclic shift and it still is a correct English sentence, even though maybe not a great one. So that's a cyclic shift, right? Every position where you could potentially put this separation between start and end gives you a different cyclic shift. Now, in general, you could have a string where there are not as many cyclic shifts that are different as there are positions, just because two of them are the same. To avoid that situation, as we've done many times before, we always throw this end of word marker at the end of the string, pretending that $ is some symbol that doesn't occur anywhere else. That means we can always recover the original string from the cyclic shift. We just have to look for the $ and put the cut right after that. So far, so easy. The Burrows-Wheeler transform now does three things, and this is the conceptual view. I will present you how you should think about this. This is not the way you want to implement it, because that would be awfully slow. But let's first understand what it is. You write down all the cyclic shifts of your text, one below the other. That gives you a matrix of characters. I'll have an example on the next slide. Then you sort these strings lexicographically. So you sort all the cyclic shifts lexicographically. And then the last column is the BWT. So again, on an example, we have this text, Alf eats alfalfa. Again, as a brilliant example, because it has lots of repetition. And in case you haven't heard this before, alfalfa is some sort of grain. I mean, it's a real thing to eat. Whether Alf would like it. So you write down all the cyclic shifts, and you can see how the $ makes its journey all the way to the front. Right? That's how you can easily see that you got everything. But this is just all the cyclic shifts. What we want to do next is sort them lexicographically. So that gives you that list. Okay. And as before, we'll treat the $ symbol to be smaller than all the other characters. Then space. This is like in ASCII, space is before the letters. Then come the A's, E's, F's, L's, and so on. And where there's a tie, you go to the next character. You know what lexicographic means, I guess. So this is a well-defined step. And now the BWT is take the last column and read these letters top to bottom. So from Alf eats alfalfa, what you get is this permutation of the letters. And you may note, or you may count, that there's $1 here, $1 here. There's a whole bunch of A's over there, and they occur as well down there. It's the same number, they just get shuffled around. Already on this tiny example, you can see there are things going on with runs. There's 3 L's and 3 A's in a row. And that's not coincidental. It's one feature of the BWT that you tend to see repeated runs of one character, the same character repeated several times. Before we dive deeper, let's think about whether you've seen something similar before. And that's this question. Maybe superficially you recognized we put end of word markers and there's some sorting going on. So that should ring a big bell about suffix arrays. But the precise statement is a little tricky, so have a quick think about this. Okay, we had 30 people voting before, so I'll probably have to leave this open a bit. Okay, 25, let me show it for now. And so here's your answers. And the right one is really B. There's some truth in saying both A and B, but that needs some extra tricks at least. So that's why I put this easily here. And I think if you say very easily for the first part, then it's justifiable to say that's wrong. Let me show you, though, what is doable, namely the other direction. How could we compute the BWT? So what we don't want to do is write down all these as literal strings and then sort them. That would be at least quadratic, just to write down all these characters, quadratic in the length of the text. And that's where we already walk away and say, no, come on, that's not good enough for us. But we can do better. We may note that these cyclic shifts are essentially the suffixes of the string. I grayed out the characters after the dollar sign here, which is just visible maybe. And if you think about it, if you compare two of these cyclic shifts in a lexicographic way, you will never compare beyond the dollar symbol because they're cyclic shifts. So the dollar symbol is at a different position in each of the lines. And as soon as you compare the dollar, you will have resolved all ties, even if the rest of the text is the same character repeated. You never compare beyond the dollar symbol. So you will never need these gray characters to decide any ordering questions. So in a sense, I could have just removed the gray characters and I would get the same sorted order on the right. That's the first observation. So we could get, with the suffix array, we could get, where do I have to start with my cyclic shift? So the 16 here means I start at position 16, the last character in the text, and then read from there, and so on and so forth. And now, how do I get this last column? That's why it's convenient in the BWT to add the entire matrix of characters, so we can just say, take the last column. But it's a cyclic shift, right? So if I go forward to the right, I go left and wrap around if I go to the previous character compared to the first one. So if I know that the cyclic shift starts at 16, what's in the last column is 16 and whatever comes before that, so 15. And the 15th character in the text is an A. So you can always do this, and that's what's written here. The ith character in the BWT is, if you take the suffix array and for position I, subtract 1, because we want to go one character before, and then take the position at the text. You have to take care of the wraparound. If you have the 0, then you have this extra special case, but the rest is regular. Okay? So this is in a sense, you can very easily compute the BWT if you are given the suffix array. Now, if you've already learned how to compute the suffix array, that direction is fine. So we can compute the BWT in linear time. Okay? So it's a good transform. It's relatively quick to compute it, even though more tricky than move to front, to be fair. Now, why is this transformation any good? Because we sort, what happens is that in the sorted order, same things are grouped. For example, you have here a lot of A's in this text. In the first column, they have to be all together because it's sorted by these strings. So all the characters, all the first column is just the characters in sorted order. And then what is going on in the last column means that this A is what comes before this, what comes after this F. So you have a context A that is fixed, and then you look at, in the BWT, what are the characters that come before this A? Or more generally, you can have several characters, like LF appears 3 times. If you look in the text, LF, 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 and the character before this LF is always A. And that's why you get 3 A's in the BWT right here. All these A's are followed by LF, and the LFs mean they are grouped together. So in a sense, what the BWT achieves is it groups characters by their context, what follows them in the text. And if there's a character followed by the same things, then it will appear as a cluster. And these local clusters of some characters being much more likely than others, this is what then is picked up by the move to front heuristic. That will mean that the move to front output has mostly small numbers in a vague sense. And the other way around, if you have a repeated substring in S, some exact repetition of a string, that inevitably means there's repeated runs in the BWT. That's the example of LF, for example. The repeated string is ALF. And if you take the first one off, LF is grouped together by the sorting, and so all these A's are lumped together. Okay? Somewhat magic, but that's the essential property. This part is what really makes the output of the BWT more compressible. To show this in action, here's a bigger example. So this is this bigger text, and here's its BWT. You see the matrices up here. And then I also applied the move to front to this one. And I think we'll discuss this at the end. All right, let's do it. There's another slightly tricky question. I do want to show you how to decode this. So maybe let's just do this let's do this quickly. The runs of H's, so this is long run of H here, which of course in the move to front then gets to a run of zeros. What can we say? Where does this run come from? I think the okay, in the interest of time, let me show you the results that you gave. There's several statements in the list of options that make some sense. The very concrete thing that we can say for this run here is, if you look in the first column, there's all these A's. Now these happen to be all A's in the text, okay? In the first column, they are all together, and these are all the A's, which correspond to all H's in the last column. So what does that mean? It means all A's are preceded by an H in this text. So whenever I see an A in the text, the character before it was an H. That's why we get this long run of H's. In this concrete text, that's the most precise statement we can make. It's also a little bit of an anomalous text because it has this strong property that every A is preceded by an H. If you have something slightly weaker, then you might not get one uninterrupted run of H, but you might get a long run of the same character, maybe with a few other characters sprinkled in. So that's why this is the right thing. The first one doesn't really explain the run in the last column. This one is the opposite. It's the context in the other direction. So what the BWT gives us is the things that come before H. It's a little unintuitive, maybe. So these two things look in the wrong direction. And H is always followed by A is similar, but again, the real statement here is this other one.